finding my camera. Why he's not finding my camera? First, when I started up Discord, he was asking for my telephone number.
Okay.
He didn't want to let me into the voice channels.
Yeah, I did up the security just before we started. Something suspicious happened.
And then the next thing is that he doesn't see my camera. But why is he not seeing my camera? Yeah.
That might be the media settings on that. So let me adjust that.
Yeah, but that must be here, I think. Because if I go to the user settings, I have voice and video. And if I go to the video, no, there's no camera. Right.
Okay. Well, just in case, I adjusted the media content filter to just see if that is what's getting in the way.
Let's see, where's my Discord now? Not yet. I go back out, go back in. No, camera is unavailable. There's nothing working now. Nothing this week. Yesterday the UPS started beeping here, and turns out to be battery failure. So okay, fine. Then this morning, the electricity, but luckily on another circuit, electricity fell out. It was the warm water heater who apparently is leaking.
Oh no.
So I switched it off, so there is no electricity leaking anymore. So later after the video, I have to go and check it. But it's an old one, so I probably will have to replace it. Otherwise, I have no hot water anymore to take a shower. And now this camera is not working. Yeah.
Well, I suspect that it was the switches that I flipped, just an hour ago. But yeah, I got 3 accounts joining within 1 minute of each other. 2 of them had the same name, and then that kind of made me suspicious. And I was looking at like, hey, what do I do to prevent like a raid kind of a situation? And one of the things is how to disable your invitations. So I went and took a look at the invites, and one of those new accounts created an invite. So I was like, okay, there's no reason that they would need to create their own invite, unless they wanted to have another door for people to come in real quick. So both of those invites are disabled, and then I bumped the moderation settings. So they have to be confirmed in order to join the video channel. And then I also there's an explicit media content filter. I bumped that up, but it must. My guess is that the filter is playing it safe with your video for some reason. But that's bumped down now. So you might actually leave, maybe even restart Discord and then rejoin.
Yeah, let's try that.
Yeah.
Let's try that. Don't run away.
Okay, I'll be right here. And to my new friends, Purger Z and Default X, if you are actually real people with no ill intent, please verify your phone number, get back on, and let's see what's going on. Just that behavior, a little bit sus. So Yeah.
No, still the same problem.
Ah, okay.
Is there an application in Windows that can use the camera? I think so. Just to check, or something on the control panel. We should be able to see settings, devices. It would perhaps not. No cameras. Yeah. Otherwise, we do it without video today, and I will check it out later. That might be.
Okay.
That
So
might be more interesting.
we'll have a deceptive lone thumbnail. It'll look like a solo, but we are actually sharing something pretty cool.
Yeah. I saw you made a lot of updates.
Yes.
And I'm struggling to keep up with it. And I tried to start on the query all in .NET, and I still didn't manage to find out where to start. So give me some hints. Where in Janaga GS should I go and look for some hints on that?
Yeah, let's put that on the agenda. We're okay, and I'll move that one to the top. That'll be what we do first. Cool. All right. Getting into Visual Studio. And let's. Why is Visual Studio not coming up? Okay, there we go. All right. So we should have Visual Studio going on. Okay. And actually, people can't see. Okay. Now people can see Visual Studio on the stream. Cool. Okay. So let's go to probably the best example to take a look at is the under not Janaga test, under Nadanga. This would be storage. We've got memory store. Memory store in the main branch is still under Janaga unit test, but I've moved it into the core Janaga library for this branch.
I saw that.
And so yeah, this implements the iStore interface. And that's exactly the interface that the Postgres provider should, or the SQLite provider should implement.
Why did you move it under the Janaga library? Because the memory store is especially for testing purposes.
I think I have the feeling that it's going to be useful for a lot more things than testing. That I can imagine a lightweight client. So maybe you're shipping a mobile application, but you don't want to do the offline support. You just want to start it out as your standard client server mobile application, and then you can gradually turn on features like offline capability and notifications and that sort of thing. So yeah, I think it might find use in real applications. So we've got save. Just take a graph, save all of the facts in the graph, give you back the list of all the graphs that, or all the facts that that were new, that were not in the database before. And then, yeah, pretty much everything else here is brand new for this branch. I guess, no, query was there. Yeah, query was there.
And load was also there.
Load was there too? Okay.
Yeah.
All right, yeah. Okay, so yeah, query, given a list of parameters for a specification to go into the given and the specification, then give me back the list of products, and a product is a tuple. It's it's a little bit more than a tuple. A product can actually have child products, so it can have collections. So it's sort of a grouped tuple. And then, so yeah, the load, given a bunch of references, just give me back a graph that contains those facts and their predecessors. So it's a complete closed graph. And then the new stuff, saving and loading bookmarks, and given a list of fact references, give me back the ones that are actually already in the database that you already know about. So
load and the save, because these are already implemented in SQLite. They are not affected, or are they affected?
They are not affected.
Okay.
Yeah, that'll still be the same signature. Yep, yeah, it's showing 0 changes. Okay, query changed. Maybe it's just looking at the history on this branch and not going back into main. I don't know. But yeah, query changed early in the branch, and then of course these are brand new, so 1 day ago. Okay, so taking a look at query inside of memory store, we can get a feel for at least how that works in memory. How that's going to work in SQL is a bit different. So I'll also show you the Postgres version of the same thing. So what it does in memory is that it creates a set of basically the starting points, then execute, match, and projections. This is where it starts to get into kind of the recursive application of this algorithm. So execute matches. We've got our starting references, and so this is the entire set of all the givens, but it's just one row. But each one is a different variable coming in, and then we start with an immutable list that has just this dictionary. So each one of these givens with their appropriate names, and then the fact references that they refer to. So we've got that in the list, and then as we go through each match, the execute match is going to return a list of those dictionaries. And so select many is going to kind of flatten over them. So basically the idea is that we're starting with one row. As we go through a match, it's going to match multiple rows, and it's going to add more symbols to that dictionary. So it's going to take the unknown that it defines, and it's going to put that into the dictionary. Now we've got multiple rows, and then we iterate through those with the next match. So that's the big difference between the in-memory version and the SQL version. Is in memory we can keep track of those those multiple results, and then pivot them and execute them one at a time through the rest of the graph. Whereas in SQL, that would be a very inefficient way to go about it.
Because you already have the full collection in memory.
Yeah.
Yeah.
Yep. So then as we get down into it, we've got our first condition, which must be a path condition. We go ahead and execute that, and now we've got, these are all of the all of the references that that match that particular path. So for example, it might be a successor join, and then we just get all of the successors of the so now we've got just one row coming in, so all of the successors of the one referenced fact that's in there. So, and the mouse just froze up. There we go. All right. And then after that, we go through the rest of them and we apply each one of those conditions as filters now to that result that we've got. So the first one has to pick out, these are the all of the possible candidates, and then if there's another path condition, then it's filtering those candidates to things that match that path as well. It doesn't execute the second path and then take the intersection, although that would be legal too. But yeah, most of the time it's going to be existential conditions, and so that's going to filter the results you've got by that existential.
So Michael, is there an easy way to have this explanation with a practical example at the same time? Because that makes it much easier to understand, not only for me but also for others.
Yeah. Yeah, I like that idea. Yeah, because this could be a reference implementation of historical modeling of the specification language. So
if
yeah,
we could have a number of a model with a number of facts where we have specification. We can say, okay, now it's that specification or that match that we are executing, that we are reading.
Yeah, it would be. So from the outside, if we come back to this, from the outside we could define a model and then define specifications inside of an interactive notebook, and just show, as we build the specification and make it a little bit bigger, we can show what does it look like, what features, what behavior does it have, and tie that back to each of the individual methods of, now that you've got this little thing, now that you've got an existential condition in your specification, now let's take a look at the code that executes existential conditions and see what it does. So it's not exactly peering into the data structure, but yeah, that's one way to go about it. Yeah, another way would be to actually just stick with this code and then write some graphviz that shows the actual facts in the model, and then so start is the collection of these references, and so we highlight those in one color, and then this is going to return, like this one here would return this set of fact references, and so they're marked in a different color.
In a way that you see where you walk through the tree or through the graph, a little bit like we did in the book in that chapter with the restaurant and the waiter.
Yeah.
And then later in the let's get.
Yeah. Yeah, actually, I think the first time that we do that is with the chess game, although that's not quite as interesting, I think.
Also, chapter 9, the query inverses.
Yeah, chapter 9 is definitely one that needs to be updated. Turns out it doesn't exactly work that way. This is so much easier to reason through. Yeah, one of the things that I do intend to do is to write a peer-reviewed math paper for a computer science journal describing this this inverse and interest algorithm. So yeah, introduce the history CRDT, and then show the particular properties of this CRDT, and then how they are implemented, and then do that proof. So yeah, and then this could be like a reference implementation of that paper. So that is that's something that's on the back burner right now. But yeah, we certainly don't want to wait for a peer-reviewed paper to come out in order to have a good documentation for this.
Yeah, but because in fact, chapter 9 was quite well explained, in the sense that you had the queries there, you had the diagrams.
Mm-hmm.
Well, I'm someone who likes diagrams.
Yeah.
I don't know why, but
mm-hmm.
it always shows how it works.
Yeah. Yeah, this code is not only lacking in diagrams, it's also quite lacking in comments. So yeah, it is a bit hard to digest this code. So yeah. Let's add that.
For the moment, we will have to do it like that.
Yeah.
Perhaps by diving into it further, I will come up with something to present it graphically.
Okay. So I have added that to the agenda. Okay. So that's how memory implements it, but it's implemented quite differently for Postgres. So let me get to, I should be able to open up a new and go to Janaga server. Yeah, that's the one to take a look at for the Postgres implementation. All right, so here inside of Postgres, we have the Postgres store, and that is using a tool in order to get its work done. So let's jump right down to the execute. Oh, okay. Sorry, Postgres store. That's all of the support stuff. Here's the real thing. Okay, here's query. Got it. No, not now. Okay, so this is using a that's doing the connection factory thing here. How it gets the SQL is it generates a SQL query from query steps. Is this? Oh, this is the old one. Okay, I might just need to get fresh code on this machine here. Oh yeah, this is way behind. Hello, Mr. Biscuits. You want to join in on the discussion today? Just please avoid the keyboard, if you don't mind. Okay. Now we've got query. That it's still using this query objects. What is going on? This does not look right. So it pulled the latest. Yes, I would like to see the home row so I can get the red keys. Thank you. So I'm on main. Yeah. And it's clean. So why is it still using join? It should just be using query should just be using specification. So let's go down to where it uses specification. Okay. Read. Oh, I wonder if okay, this might actually be halfway done. Let's start with read. Yeah, that's probably the best place to go. Lovely. Okay, so we're going to use the Sql Composer. That gets us that puts the results together. What are you doing? That's not right. Try that again. There we go. Okay. VS Code had the wrong source index, so it jumped to the wrong place. The description builder, query description. Yeah, so it's not just you that has a hard time finding the the right place. But I think this is it. Yeah, I think this is it. So what we are trying to do here is we are trying to build. Let's jump to the top of this thing. We're trying to build a query description, and a query description is specifically for a SQL database. So it's got all of the parameters for executing a SQL query. It's got things broken down into the different things that are going to create joins and where clauses and that kind of thing. So so this is kind of an intermediate step so that it can generate some text. Some actual SQL commands, yeah. Okay. So how does it do that? Is we've got our query description, our result description builder. And so presumably we've already loaded the fact types and the roles from the database, and so we've got a map that gives us for each one of those the ID that the database contains for those things. And now we so this one's got a little bit better comments, slightly better. Let me do an npm. Okay, you're about to get evicted, little kitten. Go on. Go on. Find a place to be. Yes. Lovely kitten. But
he wants to be on the first place.
Yes, he does. Okay, we'll do an npm CI. That way we can get all of this red squigglies off the screen. Okay. Okay, so we're trying to get some input descriptions here, and so these are descriptions of of one of the givens. And so what fact type is it? And so what specifically is the ID that comes from that map? What is the hash of that specific given? And then what parameters does it map to? So we allocate parameters as we go, so we can spit out the $1, $2, and then write those parameters in there. And then that label, what text label did it originally have? Actually, I don't remember if I use that anymore. But yeah, so we're just putting together those input descriptions, and then we add each of them to the collection of fact descriptions. So a fact description is going to include the inputs, but also the matches. So each of the unknowns inside of a match. And then we're putting together a lookup so that we can get a fact by its identifier. So that's just which of the facts that we just allocated up here. So this gives us our fact index, so that we can now look it up by name. And this is where we start with the query description. So give us an empty query description that just has those inputs and those facts, and then as we create the result description right here, we're going to add the other things. So let's grab all of the matches within that specification. So as a quick reminder, a match has an unknown, and it has a list of conditions, and the conditions are either paths or existential. Then also let's take the projections, and so this is going to be basically a representation of what comes after the arrow. So so once you have a bunch of tuples, how do you project those into child collections and fields and that sort of thing? And then here we've got our facts by identifier that we just built, and this path, we can get back to that. So add all of the edges, and that does a lot of the heavy lifting. So that's an important thing to look into. So this is going to go through all of the matches that started out in our specification, and it's going to look for now for each condition within those matches. Take a look at the paths and the existential conditions. So a path ultimately ends up as a join, or a sequence of joins inside of the SQL. An existential ultimately ends up as a where not exists or where exists clause inside of the SQL. And so you can see we're doing some recursion here for the existential to add all of the edges for that child query. This whole is satisfiable thing, by the way, is that we might have a specification that uses types and roles that are not yet in our database. And so if we have an existential condition based on a type that nobody has actually saved any instances of those type yet, it doesn't have a type ID, we're not going to output a where not exists clause because that clause is not satisfiable. So instead we just eliminate it. We know that none of those exist, and we just keep on going. So that's what that's all for. So that's doing some recursion. Now let's take a look at let's take a look at the path, because that's going a bit further down the tree. Okay, so we've got our inputs, and we make sure that we have an input for the label. So when we take a look at a path condition, it's got the label on the left, which is the same as the unknown. So that's not actually stored inside of this condition data structure. So then after that, it's got a sequence of roles. So those are the things that have the single line arrows. So that's just role name and then the target type. And then we've got the label on the right and its sequence of roles. So that's all we have for a path. But then what we're doing here is we are going through first the paths on the right, because that is what starts from the known fact. So we take the label on the right, we look up the fact that it's referring to, and then we start walking up its predecessors. We're ultimately going to have to reverse that. Let's see. Wait a minute. No, the right hand walk we keep in the right order. Then when we do the left hand walk, so here we grab the type and the fact index, go through that right hand walk, which we'll go over in a little bit more detail, and then once we're done with that, we've gotten up to the predecessor that it refers to. That's our new type, and so now we start walking up the left-hand side from the unknown, and ultimately we're going to have to invert that walk in order to go from that common ancestor back down to the unknown. So we go through that, and then we end up reversing those edges. So let's go over that in a little bit more detail.
Some drawings would be
very
useful.
Yeah, definitely would be. I did unit test. I did test drive this, so we've got some tests that at least given this specification, see that it generates this SQL, and it gradually builds up the SQL. So you can kind of see it from the outside again. But yeah, the tests don't give you the internal walkthrough. So yeah, now as we go through each of the different roles, so we've got the role going in there. Grab those IDs, and then determine, do we need to write out a fact for that particular point in the walk, which when you get up to the common ancestor, they're both going to get there, and so only the first one actually has to do that, and that allocates a join inside of the SQL. So yeah, we create a brand new fact index, and every time we do this, we are taking the query description, and we are adding stuff to it, but not mutating it. This is an immutable data type, so we return the new version of it, and that allows us to branch within this algorithm. So it's like, okay, you go off and do the existential condition from here. Meanwhile, I'll wait for you to be done, but then I'll have that query description, and then I'll use the old one and go down this other path. So yeah, this is adding edges to that query description, giving you back the new query description here, and this one is adding new facts and then new edges. So a fact ends up being a join to the fact table, an edge ends up being a join to the edge table. And so if we've already got a SQL alias, we've already got a join to the fact table that means that particular fact, then all we need to do is join to the edge table, reusing that same alias. But if we don't have it out, then we append it. So that's kind of the code to look through for generating SQL. Let's take a look at the tests.
Quite a bit more complicated than the memory store.
Yes. And the reason for that is that now this will, as it's doing those multiple passes, it's doing that one pass, but it's generating these immutable data structures while doing that pass. It's going to collect all of those those leaves of the graph as it's walking into a collection of query descriptions. And so that basically means you're going to have to execute all of these queries against SQLite, or Postgres in this case, and then you're going to have to merge all the results back together. So, whereas in the memory store, the complexity of the algorithm is based on the number of facts in your graph. In this one, the complexity of the algorithm is only based on the branching of the specification itself. So if you have more facts, you still end up with the same number of SQL queries. You'll just end up with more rows that you need to stitch together at the end. So avoids the whole select n plus 1 problem. Okay, so
It's actually what we saw with, I don't remember whether it was load or save, but one of these two.
Yeah.
In the memory store, it was also quite straightforward.
Yeah.
And the real implementation in SQL needed a lot more steps.
Yep. Yeah, I think that was load because of the ancestor table.
Mm-hmm.
Yeah, and an earlier version didn't have an ancestor table, but it had a recursive query. So, yep. All right. Okay, so this first test is just saying we've got a very simple little specification. So one starting point, and then we have a match with this unknown successor, and then a single path condition that just goes successor up to the predecessor. And so that is going to output a fact for the it's actually going to start with the unknowns. So this algorithm waits until you've actually referenced one of the givens before it allocates a fact to it. I think I had well, actually we just saw that it didn't. I'm trying to square that in my mind, because we just saw yeah, not the result composer, but the result description builder, build description. Yeah, it does these fact descriptions. Yeah, I think the difference is, let's take a closer look at query description. So we've got our facts, we've got our edges, and our inputs. Okay, yeah, I'm trying to square them in my mind. Why it's got F1, which means the unknown, and then once it determines that, hey, you've referred to predecessor, okay, now we're going to allocate f2 to mean the predecessor. And so that's why it's selecting f2.hash. Okay, so that behavior looks right, but this code looks wrong. Yeah, I'll have to figure out why it's doing that. Yeah, we got our inputs, we got our facts. Okay. Oh, okay, that's it right there. The fact type parameter and the fact hash parameter are 0, so we don't output the join until we've got actual numbers for that. So this adds a placeholder, so it gives us a fact index, but it doesn't give us parameters. But this one, isn't that one the index? Okay. Yeah, it's probably too much of a detail to get hung up on. But yeah, so this is going to walk through, generate a fact for successor, generate an edge E1 for this part of the path. So the role is predecessor and the type is root. And so that's based on the predecessor being f1 fact ID, and the role ID being what it looks up from the map here. And now it knows that this is root, and it can do the type checking and make sure that, yeah, you've got the right type there. And then it says, yep, you've referenced F2, so let me go ahead and add the join there. And because it's an input, I'm also going to write out this where clause. So F1 is the input. Okay, yeah. Yeah. It allocates the index 1 for the input, but it wouldn't have written it out to the SQL if there was no reference to it. So you would just have gaps in your indexes if you didn't use all of your inputs. Okay, that answers that problem. But yeah, so because that's an input, we know the type ID. We look that up in the map, and we know the hash because that's the well, SQL 4 adds that to the parameters. Okay, so that's the meat of it. These other things about producing the bookmark and sorting by the bookmark. Sorting the bookmark, but then ordering by the bookmark, and then here it's getting everything past the given bookmark. So those are extra details that need to be added to it. But yeah. So you can go through these tests one at a time, and you can see that each one adds a little bit more complexity. So this is going to add more joins. This has an existential positive existential condition in there, so this turns out to be a positive existential condition turns out to be a join. So it just continues on through, and that way, if there's nothing that meets that, then SQL is going to throw that away. And a negative existential condition turns out to be a so this is where we get now two SQL queries. So the negative existential condition turns out to be a where clause for not exists, which goes into the edges and joins in fact, inside of that condition. But first, it emits the query description that it builds up through and into that condition. So this one actually matches the deleted. So deleted is an element in this result. So F2 would be project and F3 would be deleted. Yep, right there. And then in this other one, we're doing where not exists deleted. So deleted is not part of the project, the result. So it's a parameter, but we're only returning F2. Yeah. So it's F2 is the project. F1 would have been the role. So we've got that part of the where clause, and F3 is the deleted. And that's why F3 is not in this one. So, one way to go about this would be to write each of the tests. So, just make this test compile, make it run, make it fail, and then translate just enough of this code to make that test pass.
Yeah.
And then iterate.
We'll build up step by step.
Yep.
Okay.
Yeah, so this one, I think this is based on the old, this is based on the old pipeline syntax. So you can ignore these tests, and in fact, for a time being, I want to support both of these. That's right. Yeah, the Janaga.js client still uses this stuff. So, both of those are going to remain in there for a little while until everything's switched over to the new specification.
Okay. So the Janaga.js client is still based on the old syntax. The Janaga.net client will straight away use the new syntax.
Yes.
Okay.
Yes, exactly.
Mm-hmm. Well, perhaps by using, in fact, the tests and starting with the easy specifications, it might also help understand step by step. Going through to in Janaga.js and then implementing in .NET and step by step making it more complicated.
Yeah.
And see that they compile.
Yep, I think so.
Let's try that.
Yeah. So, I have that on the to-do list to do the diagramming there. And so I wanted to demonstrate real quick the progress here. We're probably just going to have to go into this in a little bit more detail on a later one. But let me just go ahead and tease it here. So we've got in Docker, I have got a replicator up and running. And so here I'm just loading the Janaga DLL as I've just built it. So this is not yet published to NuGet. And defining a quick model that is a blog site that you can post to, and then you can change the title. if I take a look at Postman, here is my replicator. Yeah, so I can list the posts. Yeah, so I can see that this has some posts that were created right here with this date, 8/24. Let's come in here and change from the date 8/24. This is now 9/29. So we're going to do a post on replicating to the, or connecting to the replicator. So let's run that. And we've just done the j.fact with this brand new instance of Janaga client. This used to be Janaga test, but now we can do Janaga client create. And then run the query, and boom, now we've got 9/29 connecting to the replicator. Yep. So Janaga.net can call save on the replicator, which is not the write endpoint. Write is for humans. Save is for machines. But that's not all. So here I am defining a specification that given a site, I'll match all of the posts and then give me the titles that are all of the, for each post, all of the post titles. And so that produces that specification here. So now titles is part of the projection. Now when I do a j.query, I get an error, of course. Something just barely working, and then I have to demonstrate it, and boom.
Murphy's there.
Yeah. Okay.
But so it should execute the query.
Yes, yeah. So, okay. So the way that that's doing the query is not Janaga/read, because again, that's for humans. Instead, it's doing feeds, and then that's getting back this collection of feeds. And then going back through, and for each one, it is looping over feed and getting back the collection of references and the bookmark. And then as long as it has a bookmark, it's going to do this again and set the parameter b is equal to that bookmark, in this case 6, and then do that until it gets back an empty set. And so it's doing that over all of the feeds, getting all of those fact references. Then it's looking inside of its local database and seeing which ones it already knows about. And for the ones that it doesn't yet know about, then it turns around and it calls load, and it gets the actual fact objects in that entire tree.
It will call load on the server.
Yeah. Yeah. Now it's got those
load on the local database. Why?
Right. Yeah.
No.
Yeah, but then now server, once it's got those,
it will add them to the local database, and then through the watch it will update the UI.
Yes. Yeah. Okay. Well, in this case, query, it's just waiting until it's got everything in the local database, and then it's just running the query once on the local database. Now that it's got all that information joined in there, or merged in there. So j.watch is not yet working with this connection to the replicator, but there's not much more to make that work. And then it'll do exactly as you said. It will it will start the watch from the data that it has already locally, and then initiate this looping over the feeds on the replicator. And as it gets new information, then it will notify and update the UI.
Yeah.
So we see local data, and then we start to see fresh data.
Right. That is nice.
Yeah.
There is really a connection now between .NET and the JS Jinaka server.
Yes, there is. Yeah, let me try just real quick to see if this fixes it for some reason. Nope, did not. Okay. Okay. Yeah, this is probably a well, I don't know. Yeah, I'll dig into that and see what's causing that. But yeah, so it sounds like the next steps that we want to go through for next time are all about documentation. So we've got the inner workings of query execution from the perspective of SQL. That's the most important one.
Perhaps by next time I will have a little bit more understanding of how it works, and then I can I will perhaps have some ideas of the documentation, how to document it.
Yep. So grabbing that error so that we've got that. Okay. There's the error. Cool.
Okay. First thing I'm going to do is look why that camera is not working, because that icon is not good.
Yes, indeed. Yeah, might be what I did, but I did reverse it. So I don't know. We should.
I don't think it is that. It looks like locally there should be a problem. I didn't change anything, but perhaps an update or whatever.
Mm-hmm.
Let's see whether I can get image in Zoom, for example.
Yeah.
So there I don't get image. That means that there is a driver problem. Okay, Michael.
Very good.
See you next week.
Indeed. See you then.
Okay.
Thanks, Jan.
Bye-bye.
Bye.